It's a great pleasure for me to be here. So I was going to call this Toy Story 6, Philosophers Go Crazy Classifying, but I don't have young children, so I'm not sure if there even is a Toy Story 6. There may be already one. So, yeah, so the toy models, I think, are interesting cases because not many people have spoken about them, but yet people seem to refer to them a lot. Oh, it's a toy model. Even, practitioners as well as philosophers will say, oh, yes, but it's a toy model. But there's no real sort of discussion or exemplification of what a toy model is. And so when I started looking at this and trying to kind of pry things apart, I'm not actually sure that there's anything really terribly interesting to say about it. But nevertheless, I'm going to say something for 45 minutes, and then we can sort of talk about it in the question and answer period. I mean, I have some definite views about what I think are good examples of toy models, but then the question is, is that category that encompasses the examples sufficient? Because it seems like people who talk about them in a variety of different ways. So I'm very much open to suggestions and discussion about this later on, because I don't myself have a clear-cut idea of what this category should be, how it should be defined, and what should be placed in it. Okay, so I'm going to talk first about the contrast class, other kinds of models. Then look at the representational issue, which seems to be one of the big sticking points about what constitutes a toy model. And then talk about a couple of different kinds of toy models, mathematical and physical. And then if I have time, look just very briefly at simplified models in particle physics and see whether or not they qualify as toy models. And then sort of back to the beginning, see if we can get a grasp on any sort of issues related to toy models from the previous discussion. So the contrast class then include things like minimal models, caricatures, phenomenological models, and just ordinary theoretical models. And all of these are well sort of laid out or specified in the literature. So phenomenological, they're all used for different kinds of explanatory purposes, but the strategies in each case are quite different. So phenomenological models, usually what we have here is a case where we don't have a well-established or well-defined theory that will treat the phenomena we're interested in. So things like turbulence, nuclear phenomena. So the question then is, how do we account for the data in these areas, and how do we, can we make predictions in these areas? And we certainly can, but it's mostly based on phenomenological models. And both of those areas, both fluid dynamics and turbulence models and models of the nucleus are just, there's enormous number of models, phenomenological models in each of these cases. Then we've got things like idealized theoretical models. Usually those are considered like approximations that are established within a particular theory. So the ideal gas model, there's very few assumptions, and then you can make that model more realistic by adding parameters that come from statistical physics. Then we've got minimal models. Minimal models are usually ones that have the microstructure or micro phenomena washed out. So we have, they're a bit like phenomenological models, but usually in cases like this, you focus on specific characteristics. So for example, in statistical physics, where you look at phase transitions, you have minimal models that pay attention only to the symmetry and dimensionality of the system. So all of the microscopic interactions are washed out because they're not relevant to what happens at a phase transition. So you make assumptions about infinite numbers of particles, and then you calculate the critical points of the phase transition based on certain kinds of mathematical procedures. And as I said, those are usually models that depend only on symmetry and dimensionality as physical assumptions. And then we have caricatures. Caricatures involve usually deliberate exaggerations of a particular feature. They also ignore specific details like the minimal models do, but here we've got a different kind of strategy. So the goal is to isolate a particular factor and then to test robustness of the caricature under changes to the caricature. So you highlight a particular feature of the model. So you distort a particular feature in order to illuminate the importance of that feature for explanation. So an example here is Samuelson and the rationale behind intergenerational transfers of income or Social Security payments. So the idea is you assume a population of people that are completely similar, and there's only two stages, working and retirement. So we know, of course, that that's a complete distortion because some people save, some people don't, some people work part-time, some people work full-time. So there's a complete distortion of what it is to have a population of human beings where there's this kind of intergenerational transfer of income. So the caricature of the population here exemplifies presumably what's going to be important in looking at issues related to Social Security. And so we often see caricatures in political cartoons. So there was a funny one of Obama shortly after he was elected, and he was accused of being paranoid. So one of the political cartoonists made him look like Nixon. So you know immediately, if you're old enough like me to know what Nixon was like, he was totally paranoid. And so about who his enemies were, he had a list of his enemies. And so in characterizing Obama like Nixon, you sort of know immediately what the sort of what's being attributed here. So as I said, caricatures and minimal models share these kinds of similarities, but there's also distinct differences. So you ignore specific details in order to emphasize particular features of the model. But at the same time, with the minimal models, the ignoring of the micro interactions is done because it's simply not relevant. And because it makes calculation of things like critical points impossible. You just get the wrong answers. So there is a difference between saying, I'm just going to ignore this and see what happens when I use this kind of caricature, or I'm going to ignore this because it's not relevant and it inhibits calculation. Now, the thing about ignoring specific details, of course, is that's a characteristic that's common to all modeling. With phenomenological modeling, you're ignoring specific details because you don't have the theoretical foundation to incorporate them. In idealized cases like the ideal gas model, you're ignoring specific details because you don't need them. So there's all sorts of reasons for ignoring details, but every model involves ignoring details of some kind or another, or deliberately falsifying details, deliberately caricaturing the details for one reason or another. So that's sort of not an interesting way of thinking about the relationship between models or the relationships that exist among different sorts of models. So I think and this is, I think, important when we're thinking about toy models. What we need to really be looking at is not the model structure, not what the model looks like, but rather what's the motivation for building the model in the way that it's built? What's the methodology for building the model for that particular reason? And how is the model going to be used for a specific purpose? So, for example, in the caricature case, we know how to model the population because we know lots of information about the population, but we just choose to leave it out. In the case of turbulence models, we don't know how to use fluid dynamics to model turbulence because turbulence is just too complicated. So you need to instead use phenomenological models. So there's a big difference there between why it is that we're ignoring the specific details of the model and what ignoring those specific details might result in vis-a-vis the end product. So in some cases, you just might be getting the wrong answer. In some cases, you know you're not getting the wrong answer because you know you can leave out those details without hindering the outcomes. So I think looking at the sort of model structure and then trying to figure out what the model is actually, what kind of model it is really sort of a mug's game because you know, nothing interesting is going to be is going to come from that kind of approach. So, you know, there's always going to be a methodological strategy for model building, and you know, given the theoretical resources at hand, what kind of methodological strategy are you going to use? So now, so what about toy models then? How are the toy models different from these sorts of okay, there, I just need to squiggle it, yeah. How are toy models different from these kinds of models that we've just been talking about? So do I just need to?
You can go down, yeah, you can go down just
so I was doing this, I was going over.
Oh.
Before, but it's okay.
I think it's this one.
Yeah, okay, yeah.
Unless you want to go back to slide mode, the thing is that it's
yeah, okay, I'll just do that, yeah. Okay, so, yeah. Okay, so one of the things that's particularly important, well, I don't know if it's important, but it's something that's actually focused on in talking about toy models, is the representational issue. And as I said, there are a lot of people mention toy models. In the SEP article on models in science, Roman Frigg and Stefan Hartmann referred to toy models as probing models. They claim that these toy models don't involve any kind of representational function, and they don't tell you about anything interesting beyond the model itself. So in other words, the toy model tells you about the toy model. And they claim that the purpose is to test new theoretical tools that are used later to build representational models. So toy models, it's almost as though you're saying that toy models don't have much cognitive content. They're just used as a heuristic device along the way when you're not sure how to build a representational model. Then there's a recent paper in Studies in History and Philosophy of Modern Physics by Lutzak, who says, yes, I agree with Hartmann and Frigg that toy models actually don't have any kind of representational function, but they do take us beyond the model itself, and they have other sorts of functions. So they elucidate aspects of a theory. They are used for testing consistency between concepts and acting as hypothesis-generating tools. So that's more or less what Roman and Stefan mentioned in their SEP article. I'm not sure how you can elucidate aspects of a theory if you're not representing the theory in some way, but we'll leave that aside for now. He also claims that idealizations or approximations can do that as well. but they're always doing it in relation to a target system. So like the ideal gas model is a model of ideal gases. So there's a target and there's a model. The idea here is that if toy models aren't representational, then there is no target system per se, because they're not representing anything. So what they do, he wants to say, is they lead to insights by using analogies. I think there's a sort of internal inconsistency here, because if you're using analogies, you're involved in some kind of representational strategy. But my point is not to argue against this. I just wanted to illustrate it for purposes of talking about toy models. And Alex Reutlinger and Stefan Hartmann and Hangleiter have also a new paper coming out in BJPS on toy models. And they want to claim that toy models lead to understanding in two ways. One is in virtue of the toy model being embedded in a larger theoretical structure, and the other is a case where you have an autonomous toy model. So when you've got an embedded toy model, and their example of an embedded toy model is an ideal gas law, and also this the sun plus one planet model in Newtonian physics. The idea is that you can learn how actually the system behaves because you've got this background theoretical framework that's telling you all kinds of additional things about the target system. But the toy model gets its information, as it were, by being embedded in this theory. So we all know that the solar system doesn't involve the sun and one planet. But we can use that model, that toy model, to make lots of calculations and other kinds of activities because it's embedded in Newtonian physics, which is a highly successful theory. Autonomous models, by contrast, don't have any kind of theoretical embedding in them, and they instead yield how possibly explanations. So they're very much hypothetical. And their example of an autonomous toy model is a collision model that's used in econophysics. So the idea here is that agents, economic agents, behave exactly like molecules in a gas. That is, they have no desires, no intelligence, and they just run around like in random motion, like molecules. So these models are highly successful in statistical econophysics, in modeling financial markets. Because as soon as you start bringing in people's motivations and desires and goals, then everything gets very complicated. So better to just model human beings like molecules in a gas, and then you're all set. Again, here I think there's a kind of problem, because the autonomous toy model, the collision model in econophysics, gets its legitimacy from the fact that it's a reliable model in statistical mechanics. And so the idea here, the analogy is that, well, we can model populations of economic agents in the same way that we model populations of molecules in a gas. And that model was also very successful, used by R.A. Fisher in trying to bring together Darwinian selection and Mendelian genetics. The idea was you model genes in the same way that you model molecules in a gas. You assume that there's an infinite number. You assume that they interact randomly. And so that kind of model has a long history of success. So I think that it's not clear, actually, that that's an autonomous toy model at all. It's just bringing it over from another domain where it does have legitimacy and using it in another one, in another context. Okay. Now, in these cases, representation seems to be the sticking point. And so, the models don't represent. Yes, they do represent. But I mentioned in discussing some of these issues that the representation issue is not at all clear, Because what does it mean to say that you can model the theory, or that you can find out using a toy model features of the theory if you're not in some way representing the theory? Now, it's a sort of unfortunate, I don't know if it's an accident or if it's been deliberate, that we've got really bogged down in this issue of representation. You know, and there are all kinds of philosophical problems around representation. You know, well, how do models represent if we know that they're false about the systems that they're representing? But that's not a very interesting question, because every model is false, and yet many models are highly successful. So there's, you know, a million theories of representation out there. There's isomorphism, there's similarity, they've all got problems. And then there's the other issue, well, anything can represent anything. Craig Callender and Cohen's idea that, you know, well, you can use my hand to represent a quantum system. Yes, you can, but you're not going to learn anything interesting from that kind of representation. So it's not clear that, you know, yes, you can use anything to represent anything. I mean, maybe you can, but it's not very interesting. But at the same time, it's not clear that you need to have some specific theory of representation in order to figure out where the model is representing something and whether it's doing it in a good way. Because you can say, well, look, the ideal gas law or the ideal gas model represents certain kinds of gases in a particular context for that particular purpose. Similarly, I mean, you know, how do we define similarity of representation? Is it similarity of structure? Is it similarity of interactions? Is it similarity of properties? I mean, the whole thing is just, it's sort of wide open. And so I don't think that we're going to get very far if we take representation to be the point on which the debate about toy models turns. So, you know, if it's a toy model, it doesn't represent. If it's not a toy model, it might represent in other kinds of ways. I don't think that as a notion is going to do very much work for us. Okay, so given that we know now what people have been saying about toy models, what the contrast class is, what the problems with representation are, let's look at a couple of what I think are sort of classic cases of toy models, or what's been at least described in the literature in physics as cases of toy models. Well, but first of all, if we go to the Wikipedia, the sort of source of everything that's known, they say a toy model is a simplified set of objects and equations used to understand something that may or may not be part of a larger theory. Wow, well, that takes into account everything. But I think in many cases where we have really sort of interesting examples of toy models, where we've got a lot of information that's come as a result of using what's called the toy model, is that these models have actually been physical models where we've got some kind of physical analogy going on. Sometimes there's mathematical simplification, but in most cases, it is a kind of analogical reasoning. And so the idea is that the toy model or the analog is supposed to make the phenomenon more easier to comprehend. An example of a mathematical, you would call it mathematical toy model, is the Ising model, used as a toy model for ferromagnetism, or it's a simplified lattice model for a sort of toy model of a mathematical structure. And then that model is then used to explore and elucidate certain features of a theory, so ferromagnetism or other sorts of theories. So you ask then, well, what's the representational status re the target? And so the question or the the answer to that, I think, is that it's something that depends on the model itself. So the Ising model can represent things because it represents them in a certain kind of way, as a population of entities that interact with one another in a particular way. So the Ising model has a representational function, but the way that representational function is understood is in the context in which the Ising model is going to be used. So it's the way the Ising model is used, not how it's categorized. So people will say the Ising model is just a toy model, and but the term indicates a kind of modeling practice rather than, I think, the status of the model itself. So topological quantum field theory was thought for many years to be a model of real quantum field theory, but then people found out that topological quantum field theory could explain lots of interesting and badly understood features of the fractional quantum Hall effect. So when the people who discovered the fractional quantum Hall effect won the Nobel Prize, all of a sudden topological quantum field theory became much more than a toy model. So it had nothing to do with changes in the model itself, but rather it had to do with the context and the way people viewed the model vis-a-vis the way it helped people understand that particular weird effect about the fractional quantum Hall effect. Again, you have a quantum graph that's a kind of toy model for quantum chaos. So what does the graph look like? Well, it's like a network-shaped linear structure, and it's got differential equations acting on the functions that define the bonds. And it was first introduced by Linus Pauling back in the 1930s to as a model for models of free electrons in organic molecules. So it looks something like this. There's lots of different ways of representing quantum graphs, but that's one of them. And so they're naturally sort of simplified models, but you can use them in all sorts of contexts, in physics, in chemistry, in engineering, nanotechnology, and they're used mainly to represent propagation of waves in various contexts, like electromagnetic waves, acoustic waves. So something that's used as a toy model to represent particular kinds of molecules can be used to represent all sorts of things. So the Ising model and these quantum graphs represent in a way that's very different from physically based toy models. In the quantum graph case and in the Ising model, the focus is on mathematical relations that capture particular structural features of the phenomena or of the situation. Now, not that that's not the case in more physical toy models, but the physical toy models, I think, usually have many more features built into them. So I want to talk very briefly about two. One is Fitzgerald-Wheeldon band model, and the other is models of quantum magnetism. So what time did I actually start? I want to just time myself.
10, so you have until 11:45.
Yeah, so say another 20 minutes. Yeah, okay. Okay, so we've got these toy mathematical models, the Ising model, the quantum graphs, and they're very austere kinds of structures, and we learn from them because they allow us to see certain structural similarities between the physical phenomena and the model itself. Or we model the physical phenomena in terms of these structural features that the more abstract model has. But now, so now we've got a slightly different methodology when we look at physical toy models. So this is a wheel and band model that Fitzgerald built when he was interested in sort of trying to figure out what he thought was right or wrong about Maxwell's equations. And so the idea, and everybody remembers this sort of model of the ether that Maxwell constructed in his early papers on electrodynamics. Well, this is a kind of representation of that, but it's actually a physical thing. So you've got a bunch of wheels here, and these wheels this is a very elaborate piece of machinery. It was all built on mahogany, and the wheels are all made of brass, and they rotate, and we've got elastic bands. These darker circles are elastic bands. So they rotate. So the idea here is these wheels rotate in the same way that Maxwell's vortices rotated. So Fitzgerald builds this actual physical toy model of the ether. So how does it represent? Well, the spinning wheels are the magnetic field. The bands are the electric field. So when the wheels spin, the bands strain. You've got electric fields. The rotational inertia of the wheels correspond to self-induction, so that if the wheels spin at the same rate, then there's not going to be any strain on the band. But if they spin at different rates, then there's going to be strain on one side of the band. And the elasticity of the bands represents the inductive capacity of the ether. So it's all very, very clever. But each element of the model is designed as a representation of the ether, a representation of Maxwell's model of the ether, more appropriately. So what the model is used to do, or is used to illustrate the propagation of force and energy through the electromagnetic field. And so the equations that govern the model are exactly the equations of Maxwell's equations. And so Fitzgerald wants to use this to figure out what's right or what's wrong about Maxwell's equations. Now, one of the things that's wrong, and that everybody knew was a problem for Maxwell's equations, was that the potential functions that were an important part of the theory were propagated it implied that electric potential was propagated instantaneously. Now, the whole point of electrodynamics and field theory was that there was no instantaneous propagation of anything. So there was no action at a distance. So something was wrong, and so Fitzgerald wants to use this toy model to figure out what's wrong. So what the model does is it sort of illustrates the connection between the vector potential and the electromagnetic potential. And so I won't going to go through the whole thing, but the idea is the working of the model lets him figure out what the source of the difficulty is. So for Maxwell, the vector potential was a fundamental quantity, and he used it to introduce this other thing called free current density, which he defined as the divergence of the vector potential. So, but in modern field theory, or in field theory as it ought to be, the vector potential doesn't have any real physical significance since its divergence drops out, and it's just amounts to basically, choosing a gauge. So it's just assigned whatever value is most convenient. So the problem is Maxwell took J to be 0, and that's okay for electrostatics, but once you get changing fields, then J becomes non-zero and the electric potential gets propagated instantaneously. There was nothing in the model that propagated instantaneously, so Fitzgerald drops this assumption that J and the electric potential were independent, and instead redefines it in terms of the divergence of the vector potential, and makes d of the vector potential over dt 0. So what that amounts to then is just switching to what's now in modern terms the Lorentz gauge. And that completely eliminates instantaneous propagation. So what he does, very interestingly, is use this physical toy model to actually figure out what is wrong with Maxwell's equations, because the equations that govern the toy model are the equations that Maxwell's field equations, and so he uses the toy model to figure out, because nothing in the toy model actually propagates instantaneously, so there's something wrong. So but in order to do that, the whole thing has to have a very specific structure, right? There has to be lots and lots of detail built in there. And so you're not going to get a simplified model with lots of stuff left out, giving you these kinds of answers. But nevertheless, this is a kind of toy model, right? Because he builds it, he's playing around with it. It has all of these characteristics of a toy model. But it's got this very detailed and complex structure. Now, since this time, of course, toy models have grown in complexity because physics has grown in complexity. And so, you know, physical experiments are no longer tabletop experiments, and we can't use the same kind of really low-level technological instrumentation to try and figure out what's going on with our physical theories. So toy models for quantum magnetism are a good example of this. So why do you need toy models in explaining quantum magnetism? Well, because the models, the physical or the theoretical models, represent enormous challenges to simulation because they're so complicated. And they're not, it takes way too much computer time to figure out what how the model is going to behave. So what actually is what's the problem with quantum magnetism? Well, you've got these particles and they minimize their energy by aligning or anti-aligning their spin relative to each other, and that is also depends on the types of interaction between them, so a bit like the Ising model. But part of the problem is that very often not all the interaction energies between the pairs can be minimized at the same time in the same sort of spin configuration. So this is a problem that's called spin frustration, and you can't really solve this problem using ordinary computer simulation. So you can't simulate the model and hope to get the answer. So it's particularly the magnetic interactions that are frustrated. So sometimes what happens is, as I said, is the spin can't arrange its orientation in such a way that it profits from interactions with its neighbors. So you can't use an Ising model to solve this problem, and it's what would normally be the case. I mean, these sort of spin interactions are typically modeled using the Ising model. So it looks something like this. You've got spin up, spin down here. Well, how do you assign the spin over here? So that you've got so you minimize the energy. And you can't calculate that. Looks easy, but you can't calculate it. So the third spin can't gain any energy, and that frustration prevents magnetic ordering. So in quantum systems, you can't get any magnetic ordering as a result of this kind of spin frustration in particular situations. So the challenge then, as I said, to find these minimum energy configurations, the lattice geometry forbids simultaneous minimization of these energies. And so what you do is think about it like marbles on a board. How do you fill the board with red and blue marbles such that no marble has neighbors of the same color? And that's the computational problem. So that problem is not easily solved. So what do? You move to a toy model. You construct a triangular lattice of interacting spins, and watch as those spins evolve into different kinds of configurations. But how do you do that? So how do you build the toy? That's the problem, or that's the challenge. And so I think it was in 2012, a strategy was developed for doing this, where you trapped ions using electric and magnetic fields. You use a laser to cool the ions. And you cooled them into a two-dimensional triangular lattice structure with a marble at each site. So you literally take these atoms. This is like the analog of Fitzgerald's wheel and band thing, right? It's a physical process. You trap these ions, you laser cool them, and then you see how the configurations evolve. And you cool them into this kind of lattice structure. So the up and down states represent the different colors. And when the entanglement of the motions of these ions in the lattice structure can then be translated into an Ising-like problem. Or an Ising-type interaction. So you can't calculate the Ising model directly, so what you do is you sort of very carefully engineer this situation, this quantum situation, and then that lets you model, as it were, an Ising-type interaction. So you use the toy is the laser-cooled ions to model the Ising interactions. So you use that then to perform quantum simulations of magnetism. So these laser-cooled ions become like toy models, and they're often described as redefining the playground for quantum magnetism, because they provide this kind of basic toy that you can now do all kinds of things with, in addition to just talking about quantum magnetism. So they're sort of similar. This is sort of similar to proof of concept experiments, where you've got a realization, at least a sort of partly realization via the toy model, of a specific feature, which is this spin frustration. But that's very, very different, right, than when we think about how string theories are toy models of the standard model. It's a completely different kind of situation, right? One is a very highly abstract situation, and one is quite literally something that you're manipulating and playing with. So I think then some of the goals for toy models, based on the examples that I just mentioned or just discussed, they help you identify crucial features of a full model that need to be present if the toy is going to work properly. So in both of these cases, you need to know what's making the toy work. You need to have a kind of background theory in order for you to be able to actually build the toy and know that the thing is going to do some interesting work for you. Hope that some devices can be highlighted as central in the toy model. So particular features of the toy model are going to have important, I don't want to say representational, but I'll say representational capacity in order to help you explain certain things. And then they can bridge the gap between physics and mathematics by allowing an interpretation of the formalism where the physics is manifest. So the physics is manifest in in field theory. We know there's no instantaneous propagation. The physics is manifest in the quantum case, where we have spin frustration, but nobody knows how to fix the problems or how to solve those problems. And the toy model comes along and bridges the gap, almost like a little experiment between the mathematics and the physics. So all of these toy models are different, right? The Ising model, the physical models, the quantum graphs. But what is it that makes them all toys? Well, in the last two cases, it's fairly easy to see because we've got physical objects that we're sort of manipulating. Fitzgerald played with the wheel and band model. Britton used the trapped ions to simulate something else, in a way that you can use something that's not a toy as a toy, like plastic bags, right? This is not a toy. It's just written on the bag. Don't use this as a toy. Don't put it over your head. But nevertheless, so this idea is you can use these devices or these things as in an exploratory way. So what about the Ising model? Well, the Ising model is concerned with the physics of phase transitions. And basically what it does, it gives rise to, it looks at interactions that give rise to long-range cooperative behavior. So as a result of that, then it's used for lots of different things. It's used to study the growth of cancer cells. It's used to study language change. It's used as a basis for Schelling's segregation model. It's used as a model for trying to figure out aspects of business confidence, all sorts of things, because it has this basic fundamental structure in that it models interactions in a way that allows us to look at long-range cooperative behavior. So cooperative behavior where we have large systems. So it does that because it's formulated as a mathematical problem that's used to generate specific kinds of structural features. So in that sense, the Ising model is also like a minimal model, and it's often referred to, as I said, as a toy model, but it's not clear what its toy-like features are. I mean, there's nothing, if you wanted to say, well, doesn't involve a lot of detail, but it's not clear that not involving detail makes it a toy model. So I think I'm not going to talk about this because time's getting short. So back to the beginning then, what exactly are these toy models? And I've said a lot of things this morning about toy models and about why things are or aren't toy models. So, well, at the very least, they seem to come in a lot of different varieties. But the question that I guess I'm hung up on is, what is it about these models, especially the mathematical ones, that make them toys? At what point does an idealized model become a toy model? And you know, Hartman and Reutlinger have said, well, it's when it's not embedded in a theory, but mostly these models are, in some way or another, embedded in a theory. So the questions about what makes something a toy model don't seem to be answered in a generalized way, because the toy types are very different in their structure, very different in their design, and very different in their motivation. So why is the Ising model like Fitzgerald's wheeled and band model? But I think this is like the problem of classifying models generally. You know, models perform a lot of different sorts of functions. They're constructed in a variety of different ways. No model is a full description. All models have false assumptions. But those aren't reasons to call them toys. And the toy models, of course, they have false assumptions, but they've got lots of very interesting and correct information embedded in them as well. So we take all these models seriously because we think we should learn something about them. But when we're talking about how we learn something from a model, really what we're talking about is what we want to know is how it is that we learn that thing and why is it that we're learning something from that model. So I think the question about whether or not something's a toy isn't really the important one. I think the important one is, how do we use these models to make us understand something about the target system that we're interested in? And what that brings you to is an analysis of the model itself. Not a sort of putting the model in a classification. So if this is a toy model, we learn about it. We learn about a system or the target this way. If this is an idealized model, we learn about it this way. I don't think that classification of models really does any work. What's important in the classification of models is the relation of the models to the theory, the relation of the model to some other kinds of structural assumptions that we know about a particular system. So it's important to know what the relationship of phenomenological models is to theory, or what it isn't to theory. But in terms of actually figuring out what the difference is between an idealized model and a toy model, I don't think that's an interesting question that's going to really get us very far in figuring out how toy models deliver information. So there's just simply too many variables to make that designation philosophically interesting. And as a result, I think, we can, I think it's a waste of time, really, trying to figure out what makes a toy model, because for every toy model that we isolate, we can say, oh yes, but this is also a theoretical model, or it's an idealized model, or it's some other kind of model. And the representational issue is not going to get us very far either, because you say, well, it doesn't represent the target accurately. No, but it represents the target. It might only represent the target structure, but it still represents the target, or it represents the theory. It's going to have a representational function. Figuring out the representational function is going to involve just looking at the model. Figuring out what constitutes representation, that's a question, I think, insofar as we're going to learn something about that, we're going to need cognitive science for that. Figuring out how a scientific model represents a target is a sort of different kind of question, and one that is really, I think, an open-ended one. That's it for me.